Right, I have to start quickly because someone's trying to escape. Told you can meet a cat again. This is Mr. Watson. He doesn't love this right now, I don't think. He's being very patient with me. He loves me very much. Let's put him up here so you might see him. Oh, oh. What you gonna do, Watson? Oh, don't click on the keys. Gosh darn it, Watson. Alright, buddy. We love you. We love you. Oh, Jesus. Good boy. He's a fat boy. Alright, hello. Welcome back. That was fun, wasn't it? Yeah. Alright, I don't know that we need to see me up there anymore. Let's move me down there. I have to see myself as much. Okay. Welcome back. We are doing 3.2, least squares regression. We've been talking about the relationships between, well, what kind of variables are these? They're variables we can put on a scatter plot. We can put them on the Cartesian coordinate system. Well, that means they got numbers, real numbers. Maybe not real numbers. Maybe they're just positive whole numbers, but some set of the real numbers, which can be graphed on the Cartesian coordinate plane. Great. So we're doing least squares regression, and up until now in your life, well, you might have been able to do the thing we did in 3.1, describe relationships. I think that's something maybe you guys were able to do. Wouldn't be surprised if you could have done a lot of those. But the thing we're going to learn today is the step up from eyeballing it. Up until now, you've made least square regression lines by kind of saying, "Oh, that looks the best. That looks the best." But maybe we can do something a little better. Remember, I had talked about that thing called, well, maybe I haven't talked about it yet. Maybe I just hinted at it. What do you think we're trying to do when we fit that line? What would a mathematical, kind of mathematically measurable goal be in the construction of that line? What quantity might we be trying to minimize or maximize or optimize in some way? And calculus folks, you might start thinking, what could I, minimization, maximization, how do I find extrema of a function? Ooh, fun times. So consider how you can find extrema, calculus people. Put this in. Okay. So let's get into it. 3.2, least squares regression. We're going to create prediction equations. That's the first thing I want to make clear. We're going to make prediction lines. These lines make predictions. We're going to call these lines LSR lines, least squares regression. What is that talking about? Least squares regression. This isn't absolutely necessary for you to know about, but we'll be talking about residuals later on. What does a residual sound like? Residue. I don't know, like a bath residue or something, or a sink residue. Something left over. We'll be talking about residuals later. And what are we going to be trying to do with these residuals? We're going to be trying to minimize residuals. We don't want anything left over. And so we'll be talking about least squares regression. We'll be talking about residuals in our attempt to minimize them. This equation is going to look like y hat equals a plus bx. That does not look like a normal slope y-intercept form equation for a line. The statistician said, no, I don't like y equals mx plus b. We're going to do y hat, check that, equals a plus bx. So let's talk about a few things real quick. Y hat we'll always need to define. What's that hat mean? What's that hat mean? It means it's making a prediction. That means it's our predicted y value, predicted for some given x value, and x will be our, obviously our x value, our explanatory variable. Instead of y value, we should say response up here. That's the x value. Obviously, where a is the what? Well, what is a? A is a constant. What's the constant part of the line as opposed to a coefficient on a variable? The constant part's the intercept. A is the we're going to say predicted y-intercept. I'm just going to put predicted kind of in parentheses. We're going to be talking about predicted values. And B is the slope. A line, well, B, think about that. That's going to be the predicted increase. I go pretty fast. Pause this. Take your time. A line that describes how a what? How a response variable changes as an explanatory variable changes. We often use a regression line to make predictions on the response variable. You need to be just throwing this word predictions in all over the place, One point that's always on the regression line. This is a function of the calculus that we're going to kind of wave our hands around. One point that's always on that regression line is going to be x bar, y bar. The average just always happens to be on that line. Which makes me question the example above, because I would think that x bar and y bar would be something right about there. So I'm going to include that point and say let's call that x bar, y bar, the average of both the x and y, the explanatory and response variables. The one thing I will mention as to this LSR line, what's this going to be trying to do? I said least squares regression. What's this square that we're trying to minimize? The square that we're going to be trying to minimize is the difference between what we observed and what we predicted. But, of course, we're not going to just take the signed version of that. We don't want a sign on this. We want a Euclidean distance. We're going to square it. That way we just preserve distance and don't get in that issue of adding positives and negatives and saying, oh, we have zero deviation from the line. No, you just added a bunch of positive and negative things together. So we're going to have that. What's this going to do? Observed minus predicted squared. That is how far each point is from the line. But then if we square it, we could think about that visually as making a box. Okay, so this is the line that makes all of these horrible squares, because they are bad squares, folks. This is the line that makes the sum of the area of all those squares as small as possible. We want to minimize the sum of the squared deviations, the squared error terms from this predicted value. Great. So that's a little side note. You can do one day. Some of you guys, the calculus folks among you, will take a calc-based stats class. Get to do all sorts of fun stuff with that. Oh shoot, all my fun stats, grad stats stuff is at school. None for you. What's the difference between y hat and y? I think you guys can see this. Y hat, again, is going to be our predicted y value. And y then is going to be our observed y value. And understand that these then are the response variable. Cool. What do you think? Not so bad. Not so bad. We've got some equations up here. I'm going to point these equations out because somebody's going to ask me about it on the homework. If you ask me this question on the homework, I'm going to say, I told you at 8 minutes and 50 seconds or so. These are going to be a couple equations for B and A. I completely forgot they're there. Why? Because AP never asks you about these, but your homework will. So, AP won't require, but the homework will. In practice, finding these coefficients A and B for this regression line, I'm going to point something out here. These two things, A and B, these two things are coefficients. And what are y hat and x? Those things are variables. So you're going to sometimes be asked to define the coefficients. Check that. You're going to sometimes be asked to define the variables, and sometimes you're going to be asked to interpret the coefficients. That trips students up because they don't know the definitions of those two words, or they can't distinguish them in practice, or they're not looking for those differences commonly enough in practice. All right, we've spent enough time here. Moving on to the next page, you got an AP example. I'm gonna leave that as an exercise. This uses those unused equations. So I'm gonna skip it for the sake of time, and it's truly tedium. If you get to that question, the homework, where it gives you the standard deviation of x and y and the mean of x and y, you can do it if you want to, but I don't think that AP has ever asked about it, and I would just be so surprised if AP, do they even give you r? Which could, oh, that's such a tedious equation. Just skip this thing. Just skip. No need. Okay, so slope on regression equation interpretation. What is slope? Slope is the rate of change. Written other ways, y2 minus y1 over x2 minus x1. Written other ways, rise over run. Some of you might want to write it with deltas. I don't care. Delta y or delta x. Y delta x. Maybe you want to get super fancy and put some d's in there. I don't care. It's the rate of change, though. How much as the what is this? The explanatory variable. That is, as x increases by 1, the response variable, that is the y hat, is predicted. Y hat, it's got a hat on it, means predicted. Prediction, please make a note of that. Is predicted by the slope, that is, in this case, the b, we're going to say the slope. So it tells us how much we predict the response variable to increase with every increase in 1 of x. What does that look like visually as we go from like 2 to whatever, 2 to 3? It goes to something, let's say y, and then y plus b. Think about what that would look like. We're talking about point here, a point here. Let's say it went up b and it went over 1. That's what we're talking about. So, equation of a regression line. AP knows it's super tedious for you to find these coefficients A and B for this regression equation. In practice, the way this is found is by putting this data into some sort of statistical package, R, or SPSS, or you can do it in Excel. Maybe we should teach you how to do it in Excel, and it'll find that for you. So finding these by hand it just doesn't happen because we have too many data points. Do you want to sit here and type in like 3 million entries into that calculator? Do you think that's done? Do you think that's how that's done? No, that's silly. So we're not going to worry about that. We're not going to have to actually find these coefficients very often. More often than not, we're going to be given them in some sort of computer output, the way that actually this would be done. And what you're going to have to do is you're going to have to pick apart this computer output. The good news is we were going to have to deal with this stuff in Chapter 12. You know what happened in Chapter 12? Chapter 12 is dead. So we're going to just write that. Chapter 12 is dead. We're not going to worry about that. We only have to worry about these two things, A and B. The first thing's always going to be A. The second thing's always going to be B. Guys, can you do this? Can you write y hat equals 6.83 plus 0.97x? Because that's A and that's B. That's all you have to do. The first thing is the intercept. The second thing is the slope. It tells you intercept. The second thing tells you protein. What is protein? Protein must be the explanatory variable. Must be protein. What's the response variable? We're not told. So, great times. We need to be able to do that. We need to be able to pull numbers from computer output like that. They're not always going to look the same. Sometimes it'll say constant. Sometimes it'll say intercept. You need to be ready to do either. Constant is the same as A and B. Again, so the first thing is A, the second thing is B. This word COEF, that's coefficient. Okay. So identify the R value, the slope, the y-intercept, and find the regression line and state what each variable represents. I'm going to kind of do that all in one. It seems silly to split it up so much. What is the R value? R value is, well, that's R squared. R squared is 0.91. Some people in the other class missed that because they didn't move the decimal over. Mention that to you. So R, what's R going to be? R is going to be the square root of 0.91. I don't know what that is. It's, bigger than 0.91. Let's look. Square root of 0.91. 0.95. Great. There's a strong positive. How do I know it's positive? Because the slope is positive. Strong and positive. Hope it's linear, but I don't know. I don't actually know. Don't know. Would have to make that assumption. Our slope. What's our slope? It's right there. B. What's our intercept? There. A. Find the regression equation y hat equals 4.38. I don't know what I put a point there. 438 plus 0.51145x, and then I need to say that y hat is the predicted must be cost. Y versus X is the common syntax. You can't see that because of my head. Y hat's the predicted cost, and X is the... What is X? X is the income. Back out, because now I suspect that maybe my head has been blocking things all along. And so I'll back out and give you an opportunity to pause. Cool. Moving on. So the idea, we're going to have to interpret computer output. And now, I would normally have a bunch of examples to do in class, but, I don't know how many examples we need to do. Let's try this next one. Newspaper in Germany asks us to do this interpretation of the slope, and interpretation of the, identify the slope, and interpret the slope in context. Okay, well, let's do that. You can read all of this thing about German salaries, but I'm going to skip to the meat. Identify the slope, interpret the slope in context. Okay. Where is the slope? Slope is something right next here to semesters. Our slope be 1.1594. That's our slope. Now remember, this is always going to be A, and this is always going to be B. What does it mean? Well, I see number of semesters and starting salary. If I read through this, we're talking about the relationship between what? Number of semesters each person in the sample needed to complete the program and starting salary. X, Y. So what does this say? It looks like, suspiciously, that if it takes you longer to get through school, you get paid more. So the overall trend looks like that, but also notice this kind of what's going on here. This is actually part of a larger question that asks us to identify kind of the what's hiding underneath this. We see one trend, but there's actually another trend. Something going on there. Interpret this slope in context as the number of semesters needed to complete the degree goes up by 1. We predict. We are always going to use this prediction word because that's what this line does. It makes a prediction. Does it perfectly talk about all those points? No, it misses most of them. But we predict an increase. What's the response variable? In starting salary. Oh, there's my head. Starting salary of, I could write 1.1594, but it's in 1,000 euros. So I'm just going to move the decimal over 3 places and write that it's really talking about, I think this is the symbol for euros, 1,159.40. I think that's the euro symbol. We're going to go with it. I'm going to skip the... Oh, no, the next one's fun. We're going to do the next one. But then we'll get to skip one, I think, on the next page. Yep, we'll get to skip one on the next page. Do the data on IQ test scores and reading test scores give the... data on IQ. Okay, give the following regression line. We got this regression line given to us. Something relating IQ score and predicted reading score. So if we know what somebody's IQ score is early, we might be able to predict their reading score later on. Okay, what's the slope of this line? Interpret that in context. Okay, A, what's the slope? Slope is 0.882. Should be able to do this. Pause. Use the above example to write out the answer here. Pausing. As IQ increases by 1, we predict an increase in reading score of 0.882. We predict. These are predictions. These are all predictions. Remember, there's going to be some messy scatter plot of this data, and that line is not going to hit every point perfectly. That only happens in like the chemistry lab and the physics lab, where you can constrain all the variables. Can't constrain all the variables. We're talking about children and their educations. B, what's the y-intercept? Explain why the value of the intercept is not statistically meaningful. Well, our intercept here is negative 33.4. We predict that a child with IQ equal to 0, that is, x equal to 0, will have a reading score of negative 33.4. Zero IQ, that's an issue. Negative reading score. Can't have either. Can't have zero IQ or negative score on a test. Whoops. Find the predicted reading score for a child with IQ, of 130. Y hat equals negative 33.4 plus 0.882 times 130. Did I do that right? 81.26? Looks right. Great. Fun times. How much fun was that? So remember, these lines are making predictions, though. Is that child going to get an 81.26? Is that even a score that somebody can get on this test? We don't know. It's a prediction. It's a prediction. Okie dokie. Moving on. Oh, examples on the next page we can skip. Extrapolation. What is extrapolation? Inferring outside the tabulated or observed range, making predictions outside the observed values. Maybe the trend is different out there. We're going to talk about things, and maybe we can put a line to it. We can put a line of best fit to it right there. And we collected all our data right there. This is where we collected the data. And it looked super linear there. Linear looking. Ooh, looking. And maybe, outside where we didn't collect, we call this uncollected. Maybe it does something goofy. Maybe it really takes off. Maybe it goes exponential or something. And we just took data over a portion that looks linear. That's the dangers of extrapolation, extra, that is outside predicting. Cool. And we got a funny XKCD cartoon because you know I love the XKCD. Lurking variables, oh my gosh, chapter 4 is back at it. Hey, you're going to have a weird looking AP test that's going to be 45 minutes to administer online. And I don't know what it's going to look like yet, but I can almost guarantee you there's going to be a question about sampling, experiments, experimental methods, chapter 4. Go back and look at it. Go back and look at chapter 4, please. So, lurking variable. Is a variable which is not among the variables of study and influences the interpretation. Okay, you might have lurking variables here, and what like those lurking variables? Those lurking variables might help explain residuals. What is a residual? Residual is something that is left over, left behind. The residual is the distance between what we observed and what we predicted. Residual equals what was observed minus what was predicted. We're going to often write that as y minus y with a little wizard's hat on it for making predictions. Ooh. I get outside for like 20 minutes a day. I need to get outside more. God. Take a walk. Go take a walk. It's kind of nice outside. It's Thursday. Maybe it's nice tomorrow. I don't know. Positive residual means. What's a positive residual mean? Well, if a positive residual, that means the first thing is larger. I think that means the observed thing is larger. So that's observed greater than predicted. That means our predicted value is low. We would call that commonly an underestimate. And a negative residual, conversely, means predicted is greater than observed. What would we call that? We would call that typically an overestimate. So residuals and over and underestimates. Again, these would be positive residuals up here, and these would be negative residuals down here. What about this line? What's its residual? It's darn near 0. That means we almost got the prediction exactly right. Down below, a real estate agent is interested in developing a model to estimate the prices of houses in a particular large city. Takes a random sample of 25. Great. Records the price and whether or not the house is a swimming pool. Okay. Second house is a residual of 49. Interpret this residual value. Okay. Estimating the price of houses. So predicted house price equals A plus B, the square feet size. All right, so she's making a prediction of house price based on size. Residual of 49, that means the observed house price was 49, I think it's thousand. Yeah. Thousands dollar. $49,000 above the predicted price. Cats chasing one another in the background if you're curious as to what's happening. Buddy, okay? Good. All right, so we can do residuals as well. Fun times. Lots of fun. Lots of fun. Observed minus predicted y minus y hat. People love to flip this around for whatever reason. I don't know why. It's always observed first. What did we actually see? Let's continue on. AP example, got an AP example on the next page. And I am going to omit it and say, do this on your own. Do on your own. I don't want to make this lecture any longer than I can see that it's already going to be. I'd recommend trying this windmills generate electricity, AP scoring. If you Google that, you will find the answer. We've done a problem like this already, so I'm going to omit it for the sake of keeping you moving. We can make residual plots. I don't think you're going to actually have to make one, so I'm probably going to skip that in the notes. But you do have to interpret residual plots. More likely something that you'll have to interpret. Given that AP is going to give you 45 minutes total to take this test, I just cannot believe they would ask you to put in data points into your calculator. You don't know. This takes too long. We don't want to do this, AP. Okay, so we might have to interpret residual plots. And what does that mean? A residual plot shows is there a pattern in our residuals? All right, is there a pattern in our residuals? Why do we care if there's a pattern? Well, if there's a pattern, Well, what are residuals? What are residuals? Residuals, recall, residuals are prediction errors. A residual only happens if our predicted value isn't the same as our observed value. So it's a prediction error. Is there a pattern in our residuals? Do our errors change with changing explanatory variable values? We don't want to see that. We want to see random errors throughout. This looks like, okay, yeah, it looks like the errors, prediction errors, are random. This is a plot. Okay, this says we missed a prediction here by that much. We missed a prediction here by that much, by that much. Oh, come back. Good. All right, see like this point right here. This is a residual. What does that go along with? It goes along with this data point right here. It's like we took this line, watch with me, we brought it over here and we turned it. And it preserved how far each one missed by. So this is a plot of misses. Notice over here is residual. That is y hat minus y values. So residual plots might be something they ask you to interpret. What do we want to see when we look at a residual plot? We want to see no pattern in the residuals. What does that suggest? That suggests that a linear model is appropriate. But on the other hand, what if you saw a very clear pattern, say a quadratic pattern in the residuals? What does that make you think? See, quadratic pattern in residuals. What does that make you think? That makes you think a quadratic model might be more appropriate. That is, linear isn't appropriate. Maybe consider a polynomial model. Are you excited to cover polynomial predictions? Polynomial regression? We're not going to do it. In your calculator, residual plots. The residuals are something that your calculator makes. When you do linreg, it's going to make a list of residuals for you. And you can follow the steps here to do that. I am going to omit those for the sake of time, because and if you come up against a problem and ask you to do this, come to these, follow them. I don't need to belabor this. You can follow steps I've written out. Standard deviation of residuals. What is this? The average distance that the observed values fall from the regression line. Here's an equation, and I just can't believe AP is going to ask you to use it given the time constraints. So I'm going to skip it. The thing you need to know, I'm going to put a big old box around it and write by it AP template. You need to know that S is the average distance that the observed values fall from the prediction line. That is the average prediction error. I like thinking about residuals as a prediction error. How much did you miss by? A residual, kind of a prediction error. All right, so up here it gives us an S value. It tells us the S value is 3.53399, whatever, which tells us the average distance of the data points from the fitted line is about 3.5% of something on average. All right, here's our S interpretation. Here's our freaking template. On average, the distance from the, what would that be? The observed value in context to the predicted value on the least squares regression line are, this is an S, that's my clearest S, units on the x-axis. And in context, my God, all of this, all the time, is in context. You're going to learn what the interpretation of a slope is, even if you tricked your Algebra 2 teachers into thinking you did. I am going to skip part A. Part B, note that S equals 1.988. That's darn near 2. On average, our predicted, what are we predicting? Heights were approximately 2 millimeters, rounding to 2 because it's close enough, from the observed values. Neato. Moving quickly, because I don't want this to go any longer than 40 minutes, and God, you don't either. So, even though you'll have all weekend to do it, but yay, weekend statistics. We're going to skip that AP example. Coefficient of determination, percent fraction of the variation of the values of the y variable, that is the response variable, that are accounted for by the least square regression line. That is, how much does the regression line explain? Symbol for this is r squared. This is what you'll usually be given. I'm going to just circle C on the next example. Circle D on the next example. Look through these guys. I don't want to make you do this forever. I'm going to do this regression wisdom, and then I'm going to be done here. Distinction between explanatory and response is important in regression. Correlation and regression describe only linear relationships. This is the one I actually care about. Correlation. The word correlation is talking about linear things. Just don't use the word if you're not talking about linear things. The general word is association. That's general. The specific word is correlation. It's specific to linear relationships. Correlation and least squares regression are not resistant. What does that mean, not resistant? That means that outliers mess them up. A weird number, a bad data point will skew the whole thing. And last thing, association does not imply causation. Now, what do you need to do there? You need to do, what do you need for causation? What do you need for causation? You need random assignment, boys and girls. From your favorite table, the 4.3 table, that y'all are going to just go back and look at it. Just do it. Now, pause. I can wait forever if you pause me forever. What else am I going to do? I'm going to be done there. You've got some 3.2 homework you can now do. So get to getting, I guess I would say on that. Have a good weekend. It's 37 minutes. I went pretty quickly. I skipped a bunch of things. You guys can do it. Do you want to see the other cat? Where's George at? George, I'll get the cat for you. You can leave now if you want to, but if you don't want to leave, you could stay here. And you could see a cat named George. It's the last cat. And you can go to your weekend after meeting George. Oh, hello. This is Janie. And this is George. He's a good boy. He's very fluffy. It's his shedding time. Say hi, George. He's a good boy. All right. See you guys.